Okay, good morning, everyone.
Morning.
Good morning. Good morning. Do you remember what all things we have discussed in the last class? Anyone?
Bond parameters.
Yeah, bone parameters, right? Bone parameters. So, Anaga, can you tell me which are the parameters that helps us to determine its bond?
Ma'am, bond length, bond angle, bond
Yeah.
enthalpy, and bond order.
Very good. So these four are the parameters that helps us to determine the factors about bond. Okay. Then what all things helps us to find out the bond length? Lakshmi?
Spectroscopic method, X-ray diffraction, electron diffraction.
Very good. Then Abhinav, what is this bond length? Bond length. Abhinav, can you hear me? Navneet?
Yes, ma'am.
What is this bond length?
The size of an atom, like, from radius to the
Radius.
radius of next atom.
That means the equilibrium distance between two bonded atoms, right? Between the centers, isn't it? Okay, then how can we determine the bond order? Emmeline, can you tell me how can we determine the bond order?
Ma'am, spectroscopy.
When we are looking the structure of a molecule, how can we determine the bond order? Actually, the number of bonds, right? Yeah, number of bonds itself, their bond order. Then today we are going to learn about another topic, that is resonance. Okay, resonance. Are you familiar with this term? Resonance. Resonance structures? No, right? Okay, then we can learn about resonance. So according to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately. 1 minute, children. Okay. So we have learned how to draw the Lewis structures, right? In the case of ozone, you can you'd remember that there are two bonds between oxygen atom. One bond is single bond and the second bond is double bond, isn't it? So within this single Lewis structure, we cannot describe the molecule accurately. So in the case of this ozone, there are two possibilities. Just wait. You know that there is 3 oxygen atoms, and here this is double bond and this is single bond, right? Similarly, we can also draw this one as double bond and this one as single bond. Okay, so using this single structure only, we cannot able to determine the properties of a molecule completely. Okay, so and these two are the possible structures for the ozone. So these type of structures, how many structures are available for a molecule to describe its properties completely? That is known as resonance structures. Okay. Here, according to the concept of resonance, whenever a single Lewis structure cannot describe a molecule completely, using this structure 1 only, we cannot able to determine the properties completely about ozone. So a number of structures with similar energy, both of them should have similar energy, then positions of nuclei, there is no change in the positions of nuclei, then bonding and non-bonding pairs of electrons are taken as the canonical structures. So these structures are known as canonical structures or resonance structures. Okay, canonical structures, or also known as resonance structures. Of the hybrid, which describes the molecule accurately. So we can draw different structures for a molecule to learn the properties of that molecule accurately. But the conditions are it should have a number of structures with similar energy. Okay, both should have similar energy. Then positions of nuclei. Here the central atom, there is no change in the central atom, right? The positions of nuclei has not changed. Then bonding and non-bonding pair of electrons. Bonding and non-bonding pair of electrons. It has not to be changed. These are taken as the canonical structures of the hybrid, which describes the molecule accurately. So if we cannot describe a molecule with one structure, we can do different structures with similar energy and positions of nuclei, then bonding and non-bonding pair of electrons. Such structures are known as resonance structures or canonical structures of the hybrid, which describes the molecule completely. Clear, children? So this one is just an example in the case of ozone. Okay, there are two possibilities for drawing the structure of ozone. We can draw double bond and single bond at both positions, right? So these both structures are considered as the canonical structures or resonance structures. And the conditions are they should have same energy and there will be no change in the position of nuclei, and bonding and non-bonding pair of electrons should be represented. So such structures are known as canonical structures or resonance structure. Clear? That is the concept of resonance. This is not the complete structure of ozone. I didn't represent the lone pair of electrons. Okay. I will show the exact structure. Maharin, can you please read the slide about resonance?
Resonance. According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, a number of structures with similar energy, positions of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately.
Okay. Have you completed, children?
Yes.
All of you? Okay. Then we are moving to next slide. So here you can see the example of ozone. This is the proper canonical or resonance structure of ozone. Here you can see there are two structures, structure 1 and structure 2. And only difference is the change in single bond and double bond, right? And according to their change in single bond and double bond, their bond length also changes. Single bond, it is 148 picometer, and the double bond, it is 121 picometer. In the last class, we have learned about the connection between bond length and multiplicity of bond, right? It is opposite to each other. When the multiplicity of bond increases, their bond length decreases. Here you can see the single bond has the value 148 picometer. And when it comes to double bond, it will decreases to 121 picometer. So the ozone molecule can be equally represented by the structure 1 and 2. Okay, they are separated by a double-headed arrow. In both the structures, we have oxygen-oxygen single bond, then oxygen-oxygen double bond. The normal oxygen-oxygen single bond and oxygen-oxygen double bond length are 148 picometer and 121 picometer respectively. For single bond, it is 148 picometer, and for double bond, it is 121 picometer. So this 1 and 2 structures, they are called canonical structures or resonance structure. And the third structure, that's the intermediate between these two. Okay, third structure, that's the intermediate between first and second structure. It is known as resonance hybrid. Okay, first and second structures are known as resonance structure or canonical structure. And the third one is the intermediate between first and second. It is known as resonance hybrid. Clear, children? Okay. Here in both these oxygen atoms, there is a common bond length, right? 128 picometer. That's in between 121 picometer and 148 picometer. That's the intermediate bond length between single bond and double bond. So this is the example for explaining resonance structure of ozone. This is clear, children? If you have any doubt, you can ask me. Valentina, can you please read the slide?
Example, the ozone molecule can be equally represented by the structure 1 and 2, separated by a double-headed arrow. In both structure, we have ozone single bond, oxygen single bond, and a oxygen double bond. The normal single bond and double bond length are 148 picometer and 121 picometer respectively.
Then 1 and 2 are canonical structures or resonance structure. Third one is called resonance hybrid. So while drawing this third structure, you have to draw one line, this bold line, and the second one is dotted line. Okay, to show the intermediate between double bond and single bond, you should represent one line as bold line and the second one dotted line. And both the bond length are same, 128 picometer. So it's clear, children? Tell me, yes or no?
Yes, ma'am.
Completed, right? All of you?
Yes, ma'am.
Okay. Then we are moving to the next one. That's related to this ozone itself. The experimentally determined oxygen-oxygen bond length in ozone, that is same. Okay, that means in the case of both oxygen atom, the bond length is 128 picometer. Thus, the oxygen-oxygen bond in the ozone molecule are intermediate between a double and single bond. Obviously, this cannot be represented by either of the two Lewis structures shown above. That means the previous structure. We cannot represent the bond length 128 picometer using first and second resonance structures. Okay, experimentally determined oxygen-oxygen bond length in ozone molecule are same, that is 128 picometer. In the case of both oxygen atom, it will be same, 128 picometer. Okay, this bond length cannot be represented using 1 and 2 structures. So it's an intermediate between oxygen-oxygen single bond and oxygen-oxygen double bond. So there will be an intermediate structure. That's the third one. It is known as resonance hybrid. And you have to always remember this resonance structures or canonical structures should be separated using a double-headed arrow. That's indication of resonance structure. Okay. you should always draw this double-headed arrow between the resonance structures. That's the indication of resonance. And this 3 lines, it will represent the resonance hybrid. Okay. Double-headed arrow for canonical or resonance structure. And this 3 lines, it will, that means equivalent. Okay. That is resonance hybrid. Resonance hybrid. So before drawing resonance hybrid, you should draw 3 lines. That means equivalent. And double-headed arrow to separate the canonical structures or resonance structures. Because this resonance is needed for your further studies, you should draw the resonance structures of aromatic compounds, including benzene, then phenol, then aldehyde, carboxylic acid, etc. related to aromatic compounds in the coming classes. That means sometimes in +1 or +2. So you should know the concept of resonance. Okay, they are identical structures with same energy, and there is no change in the nuclei, and the bonding and bonding pairs and lone pairs should be represented, but the difference in their bond, that's the difference between the resonance structures, and it should be separated by this double-headed arrow, and the resonance hybrid should be drawn using this equivalent sign. So is clear, children? Shall I move to next slide? Yes, right? Okay. Yeah, then this resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. So when we are comparing the energy of this resonance structure and resonance hybrid, always the energy of resonance hybrid, it is less than the canonical structures. Okay. Less than single canonical structure. That's about energy. Single canonical structure. So resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical structure. So in the case of ozone also the same thing. Resonance hybrid, it is less than single canonical structures. Structure 3, it is less than 1 and 2. John, can you please read the slide? John Philip.
Resonance stabilizes the molecule as the energy of the resonance hybrid is less than the energy of any single canonical substructure.
Okay, okay, fine. Okay, have you completed, children? Then I will just show the resonance structures of benzene, okay? Just wait. The 2 possible resonance structures of benzene, you have, you know that in the case of benzene, there are alternate double bonds, right? So here, this is the structure of benzene. So its canonical structure, we can change the positions of double bond. Okay. So these 2 are the possible resonance structures of benzene. We can change the positions of double bond. Here it is between these two lines. When it comes to the second structure, it will be in another. Okay. So here the energy of both the structures, it will be same. There will be no change in the nuclei, and the bond pair and lone pair should be represented. Okay, children, and we can draw the resonance hybrid like this. There will be a dotted structure throughout the molecule. So this is the possible resonance structure for benzene. In the case of some other molecules, there will be more than two structures. Okay, when it comes to phenol, what is phenol? This aromatic ring with OH group. Okay, when it comes to phenol, etc., there will be 5 or 6 resonance structures due to the movement of this electrons from oxygen throughout the ring. Okay, so you have to know that there will be a resonance structure and they have equivalent in energy, only change in the position of single and double bond. Clear? So it's clear, children, about resonance. Any doubt, children?
No.
Okay. Then we are moving to next topic, that's polarity of bonds. Okay. Before moving to polarity, we should familiar with two types of covalent bond. First one is non-polar covalent bond. We have learned about covalent bond, right? That is sharing due to sharing of electrons, isn't it? Then there are two types of covalent bond, non-polar covalent bond and polar covalent bond. So in the case of this non-polar covalent bond, when covalent bond is formed between two similar atoms, for example, H2, then O2, chlorine, etc., the shared pair of electrons is equally attracted by two atoms because two atoms will contribute their own electrons for sharing, right? Each atom will contribute their own electron pairs. So the shared pair of electrons is equally attracted by two atoms if the two atoms are same. Okay. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called non-polar covalent bond. Okay. When the two atoms combine by covalent bond, they will share electron pairs. And this electron pair, it will be distributed equally between these two atoms. That means the representation of electron pair is situated exactly between the two identical nuclei. Okay, so the bond formed through this type of bonding, it is known as non-polar covalent bond. You can write the examples, H2 molecule, then O2 molecule, etc. Here, the two electrons can be represented like this. Okay, exact center to both the atoms. In the case of oxygen also, like this. I'm only represented the bonded pairs now. So this is mainly possible in the case of molecule with similar atoms, H2, O2, Cl2, etc.
Ma'am, can you repeat?
Yeah, tell me. Yeah, sure. In the case of covalent bond, you know that sharing of electrons take place, right? Two atoms will share electron pairs. Okay. If it in the case of a molecule with similar atoms, example, hydrogen molecule, two hydrogen atoms combine together to form hydrogen molecule. So each hydrogen atom will share one pair of electron, and this electron is equally owned by two atoms. Okay. The shared pair electrons is equally attracted by two atoms. As a result, this electron pair is situated exactly between the center of these two atoms. Okay, clear children? It's equally attracted between the two atoms. So these electron pair can be situated exactly between two identical nuclei. That means between two hydrogen atoms, the position of electron pair is same. Equal distance between two hydrogen atoms. So the bond so formed is called non-polar covalent bond. The bond formed due to the equal distribution of electrons between these two atoms, they are known as non-polar covalent bond. Clear, Aditya?
Yes, ma'am.
Yes, okay. Tom Sinton, can you please read?
When covalent bond is formed between two similar atoms, for example in H2, O2, Cl2, etc., the shared pair of electrons is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei.
Okay.
The bond so formed is called non-polar covalent bond.
So have we completed the slide, children? All of you?
Yes, ma'am.
Okay. Then we are moving to the next part, that is polar covalent bond. Okay. Polar covalent bond. So in the case of non-polar covalent bond, I told you there are similar two atoms. That means two same atoms combined together to form a molecule. Then in the case of polar covalent bond, we will discuss about two different atoms. Example, HCl, HF, etc. Here you can see two different atoms combined together to form a molecule, right? Isn't it? So in the case of this HF, hydrogen fluoride, right? The position of fluorine, that belongs to group 70. That's the right end of the periodic table, just before noble gases, right? And what about the position of hydrogen? It will be at the left end of the periodic table. So this hydrogen has a electropositive nature, and this fluorine, it has the highest electronegative element, right? Highest electronegative element. So in the case of these two atoms, fluorine has a tendency, we have learned that they have highest electron gain enthalpy, highest electronegativity, etc. So when they are sharing electrons between these two atoms, this fluorine will attract this electron pair towards itself due to its high electronegativity. Both of them share electrons for the bonding, but this fluorine shows more attraction compared to hydrogen towards itself due to its high electronegativity. So the shared pair of electrons, it will move along with fluorine. Okay, so due to this change in the position of shared pair of electrons, a partial negative charge will be obtained by this fluorine because they are accepting that shared pair of electrons. They are attracting that shared pair of electrons. So it will get a partial negative charge. Okay, and this hydrogen, it will not get the shared pair of electrons because this fluorine, they have a higher tendency to withdraw electrons from the shared pair, right? So this hydrogen will obtain a partial positive charge. So the bond formed between these type of difference in their electronegativity, it is known as polar covalent bond. Clear, children? If two different atoms combine together with a large difference in their electronegativity, the highest electronegative atom, it will attract the shared electron pair towards itself, and it will acquire a partial negative charge. Such type of bonding is known as polar covalent bonding. Clear? Okay. Okay, that's about polar covalent bond. In case of heteronuclear molecule like HF, then HCl, the shared electron pair between the two atoms gets displaced more towards fluorine or chlorine. Okay. The shared electron pair between the two atoms get displaced more towards the most electronegative atom like chlorine, fluorine, bromine, iodine, etc. Since the electronegativity of fluorine is far greater than that of hydrogen. So the resultant covalent bond is called polar covalent bond. Okay. And I told you about partial positive and partial negative charge. This is the representation of partial negative charge. And this is the representation of partial positive charge. Okay. The most electronegative atom, it will withdraw or attract this electrons towards itself. So it will get a partial negative charge. Here it's partial positive charge. So it may live with heteronuclear molecule. Hetero means different atoms combined together to form a molecule. Okay, here you can see that hydrogen and fluorine or hydrogen and chlorine, there will be a large difference in the electronegativity between these two atoms. Okay, in the case of fluorine, chlorine, etc., halogens, they are the highest electronegative group. Among this different group, fluorine is the highest electronegative element in the periodic table. So they shows maximum tendency to withdraw this shared pair of electrons or attract this shared pair of electrons towards itself. So due to this property, they will get a partial negative charge for electronegative atom and partial positive charge for electropositive atom. So these are the two types of bond, non-polar covalent bond and polar covalent bond. Vinayak, can you please read the slide? Vinayak, are you there? Devika, can you please read?
Yes, ma'am.
Yeah.
In case of heteronuclear molecule like HF, the shared electron pair between the two atoms get displaced more towards fluorine since the electronegativity of fluorine is far greater than that of hydrogen. The resultant covalent bond is a polar covalent bond.
Okay.
Ma'am,
Yeah.
what do you mean by heteronuclear molecules?
Different atoms. Okay, different atoms combined together to form a molecule. Hetero means different. So different atoms combined together to form a molecule. In the case of previous one, it is considered as homonuclear molecule because two same atoms, hydrogen atom or two chlorine atom or two fluorine atom. Here, different atoms, hydrogen and chlorine. That's why it is known as heteronuclear molecule. Clear, Emily? Okay.
Yes, ma'am. Thank you.
So shall I move to next slide? Okay. Yes, any doubt? Clear, right?
No.
Adulya, is it finished?
Yes. No.
Okay. So next comes this dipole moment. Okay, dipole moment. There is another new term. So as a result of this polarization means this attraction of shared electron pair towards the electronegative atom. Okay, so as a result of this polarization, the molecule possesses the dipole moment. Dipole moment can be defined as, it should be represented as mu. Okay, this is the representation, mu. Mu, that is dipole moment. That's the symbol of dipole moment. It is defined as the product of the magnitude of charge and the distance separating the centers of positive and negative charges. Clear, children? This dipole moment, it is evolved due to this polarization, and it can be defined as the product of the magnitude of charge that can be represented as Q and the distance between the centers of positive and negative charges. If in the case of hydrogen and fluorine, we know that this fluorine will obtain a partial negative charge, hydrogen partial positive charge. So the charge of this charge between the two atoms, hydrogen and fluorine, into the distance between the centers of this positive and negative atoms, that is R. The product of Q into R, that is calculated as mu. Okay, dipole moment mu, it is defined as the product of the magnitude of charge Q and the distance separating the centers of positive and negative charges. And its direction, it's always from positive end to negative end. Its direction, it's always from positive end to negative end. We can learn the representation, and this is the equation, mu equal to Q into R. Q is the magnitude of charge, then R is the distance separating the positive and negative centers. And this dipole moment, it is usually expressed in d by units. Okay, d by, and d is the symbol of this unit, d by. And this 1 d by, that is equal to 3.33564 into 10 raised to minus 30 coulomb meter. Okay, C for coulomb, where C is coulomb and M is meter. Clear, children? Due to this polarization, polarization means the attraction of the shared pair of electrons towards the electronegative atom. As a result of this polarization, dipole moment is evolved. And this dipole moment, it can be defined as the product of the magnitude of charges and the distance between the centers of positive and negative charges. And its direction is always from positive end to negative end. And we can write its equation mu, that is the representation of dipole moment, that is equal to Q into R. Q is the magnitude of charge, R is the distance between positive and negative centers. Okay, and this dipole moment, it is usually expressed in d by units, and its symbol is capital D. And 1d, that is 1 d by, that is equal to 3.33564 into 10 raised to minus 30 coulomb meter. Symbol of coulomb, that is C, then capital C, okay, then meter M. This is the conversion of d by unit into coulomb meter. So that's about dipole moment. Malavika, can you please read?
Yes, ma'am. As a result of polarization, the molecule possesses the dipole moment. Dipole moment nu is defined as the product of magnitude of charge Q and the distance R separating the centers of positive and negative charges. Its direction is from positive end to the negative end. Nu is equal to Q into R. Dipole moment is usually expressed in dB units. 1d is equal to 3.33564 into 10 raised to minus 30 coulomb meter, where C is coulomb and M is meter.
Okay. Have you completed, children?
No, ma'am.
Okay, then you can complete. Finish, right? Okay. Then about this dipole moment, it's a vector quantity. What is vector quantity? What's a vector? I think now you have learned in physics, right? Yeah, tell me. Aditya?
Magnitude and direction.
Yeah, both magnitude and direction, right? Okay. So dipole moment is a vector quantity. So we should show its direction also. And in the previous slide, we have discussed it's from positive to negative, right? So dipole is a vector quantity and it is depicted by a small arrow with tail on the positive center and head pointing towards the negative center. So this is the representation of dipole moment. Okay, we can write HF. There will be a bond between hydrogen and fluorine, and the most electronegative atom is fluorine. So it head towards the electronegative atom and its tail at the least electronegative atom. So this is the representation of dipole moment. Okay, you can also represent the partial negative and positive charge. Okay, the most electronegative atom will get partial negative charge and the least electronegative atom will get partial positive charge. So dipole, it's a vector quantity and it is depicted by a small arrow with tail on the positive center and head pointing towards the negative center. Children, now it's time. So I will show the slide again in the next class, okay? Let me take your attendance, just wait. Okay, children, then thank you. See you in the next class. Have a nice day. Bye.
Thank you.
Thank you, ma'am.
Thank you.